Now we're going to look at a couple of different types of natural selection that can lead to the types of microevolution that we discussed previously. So first up, we're going to discuss only 3 types of natural selection. And I just want to remind everybody that you should go back from the beginning of the semester from our talks earlier and remind yourself about the 4 requirements that are necessary for natural selection to occur. Now, if we have those 4 requirements for natural selection to occur, if they are in place, natural selection can play out in a number of different ways. And as I said again, we're going to look at just 3. Those 3 are called directional, stabilizing, and disruptive. And the first one I want to talk about is directional. And in directional selection, we start out with one particular suite of characteristics, and we move in a very definitive direction towards developing a new suite of characteristics. And I'll give you an example. If we look at the fossil history of horses, we know back, 30 to 60 million years ago that the ancestor to today's horse was a very small creature that was about the size of a dog, and it was kind of like a deer. Very small features, could run pretty fast, browsed on leaves, on sticks, etc., on trees and bushes. And so our initial distribution of individuals within the population of this particular species, you can see the body size was pretty small, and most of the individuals in the population had an average small body size. Over time, because of predator pressures and changes in the climate, it became less advantageous to be small and more advantageous to be larger. And so over the course of decades of millions of years, 10, 20, 30 million years, we had this slow movement or displacement in body size to the large end of the scale, so that by the time we got to today's modern horse, it's far larger, and most individuals in the population, their average body size is far beyond the size of the ancestor from 50, 60 million years ago. This is called directional selection. So you have selection for a trait in one direction, from small body size moving in the direction towards large body size. A second example of a type of natural selection is something called stabilizing selection. In stabilizing selection, the average or the median measurement of the characteristic is what is selected for. So I'll show you what I mean by that. Let's take for an example European starlings. These are birds that can lay any number of eggs. Some individuals in a population will only lay 4 eggs at a time. Some lay 4 to 5, and some lay more than 5. What we know is if we look at how many young survive versus how many eggs were laid, we see that there's a very definitive, over time, there's a very strong selective pressure for selecting for individuals that lay 4 to 5 eggs, because that seems to be the clutch size that survives best. If you have too few young in the nest, then, for example, those young may get cold too easily because they don't have siblings to help keep them warm, and they are more likely to die. If you have too many siblings in a nest, well, then there's literally too many mouths to feed, and some may die off anyway. The most advantageous number of young to have in the nest is 4 to 5, and you will see that over the generations in European starlings, almost all the individuals in the population lay 4 to 5 eggs. Another great example of this is in humans. If we look at the average weight of a human baby at birth, it's right about 7 pounds. If a baby weighs much less than that, the likelihood of them dying because of not having enough weight on them to survive periods of lack of food, for example, is greater, and they're also more likely to get cold and die. Now, of course, I'm talking about non-hospital situations. So think of a third world country. Babies less than 7 pounds have a higher chance of dying. Babies that weigh greater than 7 pounds have a higher chance of being trapped in the birth canal during delivery, and the mother and the child both dying. So there is a strong selection pressure in humans for babies that weigh around 7 pounds. Now, confounding that is the fact that modern medicine has made it possible for women with babies that are 10 pounds or more to give birth successfully because of things like cesarean sections and postpartum care. In other words, care of the baby and the mother right after delivery to ensure both survive. But if you take out modern medicine and you were to look just at human baby survival rates in a non-Western medicine world, you would indeed see that 7 pounds is about the optimal weight for a baby to be for long-term survival. That's stabilizing selection. Last one is disruptive selection. And in disruptive selection, you start out with a population that has perhaps 2 different colored patterns, like in these snails. And what happens is selective pressures select for both of these patterns, and the intermediate pattern between the 2 is selected against. And over time, you actually get 2 different species evolve as a result of this selective pressure. So that's all we're going to talk about in terms of natural selection and microevolution, and that will wrap it up for this week's lectures.